In this lab, we will continue with the bagging model, the random forest model. Um, so in the previous lab, we showed the random forest model using all the feature variables, and we looked at the importance of it, and we found that the predicted error rate for the test data was less than the out of bag estimate of error rate 0.1723. Now we also found that after for more than 500 trees, the error rates for the classes NRB and RB stabilizes. Now we will in this lab we will what we will do is we will create the random forest model, but on the square root of the number of predictors. So let's do that. So square root of p is the number of the predictors. Square root of p is 6.403124. Round up square root of number of predictors. Let m try equals ceiling of square root of p, and that is 7. In the following code, we produce a random forest model with 500 trees constructed. So the default for producing a random forest model is 500 trees. Construct the model on the training set using square root of the number of predictors randomly chosen. So here we need to set .seed 1, 2, 3, 4, 5. We need to pass this command because the random producing the random forest model, the command produces the random values. So to keep it the same for the values produced, we set the seed. Let R1 equal random forest of class and that equals to addition of all the predictors, but where the number of predictors is square root of p, where it is 7 on 7 predictors, and they are randomly chosen, comma data equal train, comma m try equals 7, comma importance equal true. So that produces the random forest tree, and the number of trees default is 500. Number of variables tried at each split is 7. Out of bag estimate of error rate is 0.1591%. Confusion matrix. Misclassification of observed NRB is 53, and misclassification of the class RB is 31. The out-of-bag estimate of error rate for random forest model on square root of the number of predictors is less, which is 0.1591%, then compared to when all the predictors are used, and is the reason why the random forest fits a better model on the square root of the number of all the predictors. Now let's check the error rate of this new model. Head of R1 at a dot rate is gives us this. In the following code, we plot the error rates of fitting 500 trees to the random forest model. Plot R1, comma main equal error rates, legend top right, comma legend equal call names of R1 at a dot right, comma LTY equal 123, comma call equal 123. So we get this. So we can see that the error rate for RB is higher than the error rate for NRB class. And after 500 trees, for more than 500 trees, the error rate for NRB and RB stabilizes. The plot shows that 500 trees are good for estimating errors. As the error rates of classes NRB and RB stabilizes, and there seems to be very less variation in error rates for more than 500 trees, the black curve for the class out of bag represents the out of bag misclassification error rate depending on 500 trees used. In the following code, we find the three most important variables in terms of accuracy according to random forest. Importance of R1. Print the first few rows of the importance of the model. So head of importance of R1 prints the first 6 rows, and we can see this. Let's find the three most important variables. So to do that, we need to look at the highest accuracy for the variables. So we look at the mean decrease accuracy, which is the third column. So let var equal to sort of R1 at importance column 3, comma, decreasing equal true. The three most important variables are SPmaxL, SPmaxBm, and SM6BN. Compared to the bagging method, where all the variables are used to create the random forest, SPmaxL and SPmaxBm are chosen by both methods. var from 1 to 3. So we are printing the first three names. So we get this.